Dear students, previously we discussed the symmetrical SN2 reaction. In this, we have seen one example, that is a tertiary butyl cyclohexyl iodide. Okay, this compound is a cis tertiary butyl. Okay, 4 in the 1, 2, 3, 4th position is the tertiary butyl. And second example, in symmetrical SN2 reaction, we have taken cyclohexyl iodide. Hexyl iodide. This example we have discussed under the symmetrical SN2 reaction. Okay, in this we are familiar with the mechanism of SN2 reaction. If suppose we have the compound CH3Br and we use KOH, okay, then this compound, that OH minus, that's the hydroxy ion, attack this compound from the opposite side of, this is our leaving group, opposite side to the leaving group, and this is a attacking group, and that is our leaving group. The transition state we have seen like that. In SN2 reaction, bond breaking and bond making takes place in a single step, and that single step is a rate determining step. Okay, therefore the one groups, that is nucleophile attack, takes place opposite to the bromine or bromide group, and this is our planar group. Okay, suppose this is a planar group. At this point there is a bromide group is there, and therefore this side is totally blocked. Therefore it appears from the opposite side, OH minus. There is a, or opposite, in this case if there is a bromine, back side is bromine, then this side is empty, then nucleophile attack from that side. Okay, therefore opposite to the bromide, OH minus attack takes place in this SN2 reaction, and that is its mechanism. Now we have seen already this compound when we used in this compound iodide minus as a nucleophile. Okay, as we know that in SN2 reaction, attacking group and leaving group simultaneously attacks nucleophile, and leaving group simultaneously break. Okay, therefore if it is a cis compound, our iodide minus will attack opposite side from the iodine or iodide, or in this compound iodide I minus attack from the acyl, and this is from the equivalent. Okay, therefore the transition state is obtained for both reaction is the same. Okay, because from the acyl side there is iodide group and iodide minus attack from this side, therefore both groups are the same. Okay, therefore this is we studied under symmetrical SN2 reaction. Okay, in this case you found that the energy of transition state of both cases, okay, when you consider both cases, it's same, and therefore its energy is same. Okay, transition excited state energy for these two molecules are same. Okay, now the ground state energy, okay, for this molecule and this molecule. Okay, for these molecules we consider this is at the acyl one, iodide is at acyl, Therefore acyl, if in hexane there is a acyl position group is there, then therefore there is a 1,3 diaxyl interaction takes place. And also this is the bulkier group, okay, tertiary butyl group, big group, there is a 4 carbon group, then there is also this interaction is also same side tertiary butyl group, same side iodide is there. Therefore this compound has the higher energy. Okay, by looking its conformation and by looking the where the group is placed at the acyl or at the equilibrium, we can predict the is it higher energy or is it lower energy. Okay, this compound is higher in energy than this. Therefore ground state of this energy is higher. Okay, cis compound ground state is higher, and for our trans compound ground state, okay, its energy is less. Therefore the energy is less, we written at the bottom than this. Okay, then transition state for both compounds are same. Okay, therefore this is a transition state energy. Okay, this energy is same, we written like that, same way. This is a trans, then the difference, this is our, if it is a acyl, okay, this compound is an acyl compound and this is the equatorial one. Okay, therefore delta F for acyl and delta F star for the equatorial. Okay, and this energy our Fa energy and the Fe energy. Fe minus Fe is the, okay, excited state energy is the 0 in this case. Okay, therefore, and this difference between ground state, this is delta F, that is the free energy. Okay, this is called the free energy. We discussed previously this. Therefore, the difference between the activation energy in this case is nothing but its difference in the ground state, that is the free energy. Free energy difference of the compounds, that is the activation energy is nothing but the delta F value. Okay, for symmetric case it is somehow easy because the transition state are same, have the same energy. But when you have the unsymmetrical SN2 reaction, then the transition state has not the same energy. Therefore it is somehow when compared with the SN2 reaction, it is difficult to understand. Okay, therefore, for the understanding, we have two examples. That is, the first is the 4 tertiary butyl tosylate. Okay, our first example, 4 tertiary butyl tosylate. Okay, 4 tertiary butyl. Okay, this is cis1 cyclohexyl tosylate. That is a cis compound. Okay, that is because these two groups are the same side, at the acyl and the equatorial. Now, second, its isomer is that's the trans isomer. Okay, this isomer is trans tertiary butyl cyclohexyl tosylate. Okay, we are in this case comparing the which isomer react faster when SN2 reaction happen. Second example we have is a 4 tertiary butyl bromide and 4 tertiary butyl cyclohexyl bromide. Okay, this is our trans compound and this is the cis compound. Okay, we are comparing in this case which compound react faster. Is this compound react faster than this or this react faster than this? Okay, therefore we add our thiophenolate ion. Thiophenolate ion acts as a nucleophile. Okay, in fourth reaction acts as a nucleophile. Okay, as we know that its transition state. Okay, transition state will decide the which compound react faster, which isomer react faster, whether trans isomer react faster or cis isomer react faster can be decided by using the transition state. Okay, in this case cis isomer bromide group is at axial position, then your thiophenolate ion is attacked from equatorial side, because this side is the blocked side because bromine is present. Okay, as we previously discussed in its mechanism, the nucleophile attack from the opposite side of the leaving group. Okay, now we have shown like break, bromine is break and SPH is attack in transition state. Simultaneously it breaks bromine and the SPH will be at the equatorial position. In this case you can show the bromine is at the equatorial, therefore attack of thiophenolate ion from the axial one. In this case your OTS is at axial position and attack of SPH is from the equatorial, therefore OTS and opposite to the SPH. In this case transition state looks like that, OTS at the equatorial and at this stage there is a SPH attack is there. Okay, when you compare these two things, you found that in first case it is a smaller group, bromine is a smaller and this is the bulkier. Remember, bromine is a smaller and SPH is the bulkier group. In this case OTS is the bulkier group and SPH is a smaller group when compared with to each other leaving group. And the two conditions we have discussing, the one is the smaller group and other is the attacking group is the smaller in first case, bulkier in first case, and attacking group is the smaller in second case as compared to the leaving group or departing group. Now we predict the ground state energy for each compounds, whether trans having the higher energy or whether cis having the. Okay, this ground state energy we can predict by its conformation, whether your group is attached at the equatorial position, whether your group is attached at the axial position. Okay, in this case you found that there is an axial group is there, therefore 1,3 diaxial interaction will be there, and also in this case the bulkier groups and the bromine groups there is a such kind of repulsion is also there. Therefore this group is the somehow this energy of this group ground state is higher than the energy of this group. Okay, same we can apply in this case, energy of this is higher than the energy of equatorial. Okay, now therefore energy of this is the higher, therefore we can write this somehow, the energy is higher and the energy of this is the lower in case. Okay, therefore this is our axial substituent and this is our equatorial, therefore we given the name ground state A and the E. Now consider its transition state. Okay, when you consider the transition state in this case, okay, when your SPH is attacking from the from top side, okay, in this case SPH is attacking from the top side, therefore this SPH or this SPH in this, okay, we are attacking from this side, therefore this SPH filling it is a bigger and bulkier group filling 1,3 diaxial interaction, okay, during when you attack from the axial position. Okay, therefore this is filling and it is also there is a bulkier group interaction is there from the SPH is attack from the opposite side of the leaving group. Therefore in this case the transition state energy of this is the, because in this case bulkier group at the less bulkier group at the axial one and the more bulkier group at the equatorial, therefore in this case less energetic, this is the less energetic TS than the other. Okay, TS energy is the less for this compound than the TS energy of second compound. Okay, this we have decided according to the substitute. Where is the substitute, at the equatorial or at the axial one? Okay, therefore in this case we found that when your group is equatorial, then in this case you found the 1,3 diaxial interaction. Okay, 1,3 diaxial interaction when you attack group from the axial side. Okay, now therefore its energy is higher. We can write this energy somehow. In this case, energy is the higher one for equatorial one, and its energy for the axial one is the lower. Okay, therefore this is energy difference, activation energy difference. Therefore delta F star A for the axial stand for delta F star F, delta star F E. Okay, and this excited state energy is the F A, and this is the F E. Okay, when you find the delta F star E, okay, this is higher energy, F minus delta star F A is round about 24 kilocalorie per mole in this case. And the energy difference from the ground state difference, okay, that is ground state difference, energy ground state difference is equal to 0.7 kilocalorie. Okay, this difference delta F, okay, free energy difference is equal to 0.7 kilocalorie. Okay, when transition state is same in symmetrical, then this energy is the same. Okay, you can show this energy at the same level, but in this case we cannot show the same energy level. Okay, now this is the energy difference of the excited state, that is the Fe minus Fa. Okay, total difference of the this is equal to 2.5, and this is less than the delta F. Delta F is the 0.7 kilocalorie per mole. Therefore, this difference Fe minus Fa is given by 2.4 minus 0.7 is equal to 1.7 kilocalorie per mole. Okay, this difference we can find 1.7 kilocalorie per mole. Okay, excited state difference. Therefore, in this case, you found that the activation energy for this compound, okay, is the less. Therefore, it react faster. Okay, cis isomer of one tertiary butyl cyclohexyl bromide react faster. Cis isomer in this case react faster. It gives the fast reaction. Okay, when this situation we consider the when departing group is the smaller and attacking group is the bigger group. The second situation we have consider OTS is the bulkier and attacking group is the smaller. Okay, in this case, your for transient state energy and transient state energy of second compound, we found that this is the bulkier group. Therefore, in this case, 1,3 diaxial interaction found there. Okay, compared to this is the smaller group, and compared to this is having the small 1,3 diaxial interaction. Okay, therefore its energy is the higher energy than the transition energy of equatorial. Okay, like that way we consider the, okay, in same case also when your axial group is there, SPH at the attack from the lower side. Therefore, in the SPH attack lower side and SPH attack upper side, because OTS is opposite side. Okay, therefore first energy, this is having the higher energy than this energy. Okay, therefore it is at axial one, and this is at the equatorial one. Okay, now a transition state energy, it is also higher. Okay, therefore we can write the transition state is higher, we can write like that, and transition state for this is lower than this compound. Okay, therefore we can write like this. Okay, by clearly observe, by observation you can find that the transition state, this is the delta F star A and this is the delta F E star. Okay, in this case also, okay, you found that the energy of this is the higher, you can written at this position, and it also the axial energy is higher, you can write. In this case also, if equatorial energy is less, therefore equatorial energy is less. Okay, but you found that in this case the OTS is at the bigger group, therefore it shows the 1,3 diaxial interaction. In this case, when it is axial, therefore it's higher, it shows the higher energy, that is the FA is the higher than the FE energy. Okay, now the ground state energy also, delta F is also same 0.7 kilocalorie per mole. Okay, as like in when substituting is the bromine, same 0.7 kilocalorie energy is there, and in this case also the difference of between ground state is the 0.7 kilocalorie. It is the same in this case also. Okay, but when you found this difference, okay, total difference of delta F star E minus delta F star, okay, that is the difference. Okay, therefore activation energy, okay, instead of the activation energy difference is equal to 2.1 in this case. Okay, therefore this minus this, when you add, there is a, when you add the 0.7 to this, then from this to add, when you remove the this, therefore this energy difference, okay, delta FA minus FE is equal to 2.1 minus 0.7 is equal to 1.4. Okay, in this case the energy is not as much more than this. Okay, in this case 1.7 is different, in this case very less, 1.4. Also in this case the activation energy difference is the 2.4, in this case less, very less is there. Okay, by considering all these factors, okay, by considering all these, you found that the energy difference is not more in this case, and therefore these two molecules reaction rate is comparable. We could not say whether it is react faster, whether it is, okay, there is a comparable energy rate in second compound than the first compound. Okay, these are the two compounds we see for the unsymmetrical SN2 reaction. I hope you get the idea about this and you understand this concept. Thank you very much.